Alright, there you have it. Today we are solving problems on colligative properties. They said question 5. The vapor pressure of water at 50 degrees C. Vapor pressure of water, Vp, at 50 degrees C. This is how I write my own. Vp of H2O is 12333 Newton meter per second. Please always try your best not to convert anything. At this temperature, I remember our class the other time. I told you that anytime you're given vapor pressure of a particular thing, they tell you the pure vapor pressure, they tell you that the vapor pressure of something at a particular temperature, you first of all need to know that it is likely to be the pure vapor pressure. Then at this temperature, a solution of urea is having 9.14 gram in 150 gram of water. So water is having 150 gram. Then water has in 150 gram of water has, okay, they said at this temperature a solution 9.14 gram of carbamide in 150 gram of water has a vapor pressure of, so P, that is PA, or you say P of solution. I like you to be thinking of it in this way. Always think of it in terms of vapor pressure of solution and then vapor pressure of pure solvent. So vapor pressure of solution is 12,106 Newton meter per second. Then they're asking us to calculate the molar mass of urea. So remember that this is W for solute, W2. This is W for solvent, W1. Then naturally we should know that water has molar mass M1, which is H2O, that is 1 times 2 plus 16, which is equals to 18 gram per mole. Now if I know this, I will start plugging in things. So that means that what I'm using to solve this question is simply when they are assuming what they gave me is maybe temperature of, maybe elevation temperature, or maybe freezing point temperature. I will use freezing point to solve, or the elevation or osmotic pressure. But what they gave me is vapor pressures, and then they're asking me to find molecular mass. So I will take it that this is when I am using vapor pressure, relative lowering of vapor pressure, to find molecular mass, and that is simply P naught minus P all over P naught is equals to W2 M1 all over M2 W1. So if I plug in, I'll have P naught is 12333 minus, I have 12106 all over 12333 is equals to W2 is 9.14 gram, then times M1 is 18, that is molar mass of water is 18 all over, I don't know the molar mass of urea, that is what they asked me to find. Then W1 with mass of solvent. Mass of solvent given to me is 150 gram. So I know that I can simply, to make things easier for me, I can simply do cross multiply, so that I have 12333 times 9.14 times 18 is equals to 12333 minus 12106 times M2 times 150. So let's punch it. Pian, let's punch. So 12,333 times 9.14 times 18 is giving me 2029 Is it 2000 I'm seeing there? That is 229,025.16 equals to, let's do this, 12,333 minus 12,106. I have 227 into M2 times 150. And you know that this is going to be the same thing as saying 227, or you say 227 M2 times 150. This is the same thing as saying 150 times 150 M2. Then capital M, please. So let's do this. So this is going to give me the same thing as saying or we can do, I think, instead of getting confused, we can do by the time I get it, I do 150 times 227. It will give me a value. Let's do it. So I have 227 times 150. I have 34,050 M2, and all equals to 2029,025.16. So divide both sides by 34050 to get M2. So M2 will become, so you get 59.5895. So molar mass of solutes, M2, once you see 2 here, always know it's for solutes, it's going to be 59.6, or I can even say M2 is approximately 60. And it's going to be gram per mole for molar mass. So that is the answer. That is how you go about it. So remember that when you are finding molar mass using relative lowering of vapor pressure, that's the only time you don't introduce any of those cryoscopic constants or ebullioscopic constants, because in boiling point and freezing point, once you introduce ebullioscopic constant and cryoscopic constant, you always introduce 1000 to it. So this is the answer. Let's look at the second question. The next question, so state 3 limitations of boiling point method for finding relative molecular mass. I've said it now. There must be no reaction. No dissociation or association. That is, no ionic molecule. It should be involved or should take place. Then it must be diluted solution. Then you have to have non-volatile solute inside volatile solvent, so that at the end of the day it's solvent that is doing the evaporation. Then when it has to do with freezing point, only a small part of the freezing or say the ice has to break away to show that solvent is more. Okay, now they said the elevation of boiling point of a solution depends on elevation of boiling point of a solution. It largely depends on solutes, because it's when you add solutes that temperature will have to increase. It will take more time to get to that boiling point. So ebullioscopic definition, I've said it before. I said that it is the elevation of boiling point when 1 mole of solvent, when 1 mole of solute is added to 1000 gram of solvent. Okay, so look at it, Beckham's, Lanham-Beggar's and Cottrell's method. Okay, let's go back to solving this question. The next one, they said solution containing solution containing 103.8 gram solvent of sucrose. Solution containing 103.8 gram of sucrose dissolved in 1000 gram of water is to have a density of blah 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 at 101.038 gram per centimeter at 20 degrees C. Assuming the density to be independent of temperature, calculate the vapor pressure of the solution at 100 degrees C. The boiling point of the solution, they now give us, we should calculate the boiling point of the solution. They now give us things like this, that we should take pressure of this, all these things. Let's solve it. So this is the question we just finished, remember. So this is the one we are solving now, which is question 10. And I think we've solved this in class. So let's try to do it. So solution containing 103.8 grams sucrose. So sucrose is a solute, not solvent. So solute there is equals to, or you say, let's be using W. W means weight, mass. W2 is for mass of sucrose. So it's 103.8 gram. The molar mass of sucrose is given. Sucrose is given here. So M2 is going to be C12H22O11, which is the sentence saying 12 into 12 plus 1 into 22 plus 16 into 11. This should give me 342. Now, for M1, W1, 1000 gram of water, that is W1, solvent, mass of solvent, 1000 gram, is to have a density of, all those blah 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 is of no use to me, because they said assuming the density to be independent of the temperature. So water, even if they did not give me the molar mass of water, I need to know that M2 for water, which is always the solvent, is simply H2O, which is the sentence saying 1 into 2 plus 16. So they said we should calculate the density. And remember, okay, that we should calculate the vapor pressure of the solution at 100 degrees C. So they are giving us temperature to be 100 degrees C. And I don't use 100 degrees. We don't use 100 degrees, the Celsius, we use Kelvin. So plus 273 Kelvin, which will give us 373 Kelvin. We always use temperature in Kelvin. All right, even if they did not give me the pure vapor pressure, but they gave me, once I'm dealing with this and they're asking me to calculate the vapor pressure of solution, that of the solvent will always be, since it's water, will always be its vapor pressure at 100 degrees C, which is 760 millimeter mercury. So here is given to me. So I will simply use it. They said take vapor pressure of pure solvent to be 760 millimeter mercury at 100 degrees C. So I will simply use it. So P naught is 760 millimeter mercury. The only time you convert units in chemistry is when maybe they gave you one thing to be in this unit, then gave you the other one in another unit. So applying the formula, since what they are talking about here is to calculate P of solution, that is vapor pressure. That means it's the same thing as saying relative lowering of vapor pressure is equals to W2 M1 all over M2W1. Very important. So if I know this, I'll just plug. So I have 760 minus P all over 760 is equals to W2. That is mass of solute 103.8 times molar mass 342. Should be? Let's check. 342. All over M2. Jesus. M1 is 18. Are you mad? God. It's 18. Sorry about that. All over M2. I wrote all these things out now. How come I... Yes, that's the mistake. M1 is M1, molar mass of solvents. 1 for solvents. 18. Then M2 is 342 times W1 is 1000. So if you do this very well, let's try to punch. If you punch this, you have 103.8 times 18 is equals to 1868.4 all over 342,000. Yes, so 342,000. So if I know this, we can now divide. Let's divide. So I have 1868.4 divided by 342,000. So I have 0.00546. Then I have 760 minus P all over 760. So this is going to give me cross multiplying. So this is going to give me 760 minus P is equals to 760 into 0.005463. So I have 760 times 0.005463. Yes. So I have 4.15188 is equals to 760 minus P. So I know that making P subject of the formula now means this will have to cross over. So I have minus P equals to 4.15188 minus 760. So minus 4.15188 minus 760. So I have negative 755.8. So you can see this can cancel. So P, the vapor pressure is simply 755.8, which is approximately 756 millimeter mercury. So it's going to be 756 millimeter mercury. 756 millimeter mercury. So vapor pressure of solution is 756 millimeter mercury. That is P of solution, remember. That is what they asked us to find. So if I know this, this is 7. All right, if I know this, let's check the question. The question still asked us to, the question still went on to ask us to find the boiling point of the solution. And they gave us Ke 0.52. Assuming they did not give us, we can still find it using what we have here. So remember that Ke, they said find the boiling point on the solution. So the II. So once we are talking about boiling points, remember boiling point is equals to Ebullioscopic constant times mole fraction of solutes times 1000. And remember that this Ebullioscopic constant is given 0.52. In a situation where it's not given, you use Ke equals to R. R here is given. Use R T naught. That is pure temperature of pure solution square all over 1000 times latent heat of vaporization. To find Ke, but is given. So Ke, and remember, this one is giving us, they give us this to be 0.52. And then mole fraction, we remember that mole fraction is the same thing as doing W2M1 all over M2W1. So times 1000. So all we just need to do is to go back and substitute all the values we have to get our TB. So from that question, we got that W2 is 103.8. So 103.8 times M1 is 18 all over M2 is 342 times W1 is 1000. Is 1000. So times 1000 times 0.52. Alright, so let's punch. Let's try to punch this. So 1868.4 divided by 342,000 gives me 0.005463 times 1000 times 0.52. So we have, let's do it, 0.52 times 0.005463 times 1000. So we get elevation of boiling point to be 2.84076, which is approximately 2.8 TB. So 2.8, and this is going to be in Kelvin. If you remember, that's what we used in Kelvin. So we can still remember that TB is equals to for elevation of boiling point is equals to T1 minus T naught. And we know that T naught here, if you remember, T naught given to us is when it's in 100 degrees C. 100 degrees C, so 373. So which means that this is the same thing as saying 373 minus T1, then 2.8. So making this subject of the formula, we get T1 to be equals to, if this cross equality sign, it will become 373 plus 2.8. So I have 373 plus 2.8. So this gives me 375.8. So the increase in temperature is actually 375.8, while the boiling point is 2.8 Kelvin. I seen it. And if we have this 2.8 Kelvin, let's say this is what you have, but I like to do it in such a way that when we do this, if you go to your textbook, you'll still not be wrong. But you notice that in most cases, like if you go to your textbook, you notice that they make it such that TB is equals to KEW2 all over M2W1 times 1000. So this is more like they are keeping the molar mass of solute constant. They are taking it to be a constant, that of the solvent, molar mass of solvent to be constant. So if you use this formula, this is what you are to be using. So if you use this formula now, you have that this is the sentence saying, using this formula now, I'll no longer put the sentence saying getting rid of this times getting rid of this 18. So let's try to do it without this 18, because that is our M1. So it is kept constant. Then it now have 0.52 times 103.8 times 1000. So I will get up here. I get up here to be 53,976 all over 342,000. So divided by 53,976 divided by 342,000. So I'm getting 0.157. So I get 0.158 approximately 0.158 as the TB. So but notice that here we got 2 points, so we won't use this. Reason being that the M1 is kept constant. The M1 is kept constant. That is from this formula. This M1 is kept constant when we are calculating. The molar mass of solvent is kept constant. I forgot to even include that in the other video. Molar mass of solvent is kept constant. And the reason for that is this. Let me show you why. I said, considering different weights of solutes dissolved in the same amount, in the same solvents, then the elevation of boiling point is proportional to the weight of solutes dissolved in a given solvent. That is change in T directly proportional to W2. So we have no reason. Then they say consider the number of moles of different solids in a given weight of given solvent. Then the elevation of boiling point for 2 will be equal. Let the elevation of boiling point when we dissolve 1 mole of solid in 1000 grams of solvent. Let the constant be Ke. Then the formula below is generally accepted. So this is a generally accepted formula. That is based on laboratory experiments. Not like the other one is wrong, but this is what is accepted. So 1000 KEW2 M2W1. So you see that the M1 that is supposed to be here is constant. So that is it. So if I know that, so this is our answer for boiling point. So the boiling point is actually TB is equals to 0.158. So if I apply TB to be equals to T1 minus T0, I will get 0.158 is equals to they said this one is at 100 degrees C, shebi. 100 minus at 100 this is going to be T1 minus 100. That is the temperature for boiling of solvents, 100 degrees C. Then, so if I make this out of the formula, it becomes T1 equals to, crossing over, it becomes 0.158 plus 100. So that's for the increase in the temperature. So if you punch it, you get the increase in temperature. That's not the boiling point, but the increase in temperature. And that increase in temperature is what gives you the elevation of boiling point. So we have 0.158 plus 100. So it gives you 100.158 degrees C. So T1. So this is our elevation of boiling points. So this is elevation of boiling points. Very important. So that's the increase in the temperature. So if I know that, remember the reason why we did this. We have the boiling points. That time we did change the boiling points. We did such that from the boiling point of the solvent and that of the increase, we say that elevation of boiling points gives us T1 minus TO to get the difference. So if we get this boiling points, change in boiling points, this is change in boiling points. If we get it such that we have this and then we have this, once we are able to get what the difference in the two is, we get change in boiling points, which is elevation of boiling points. But in a situation where this now is giving me an increase, that means this boiling point elevated. So it increased from T0 to T1. You see it. So for that solute that was added, the temperature that it exhibited is this one, T0. At the end of the day, it's added increase. Remember our graph. When we did this graphing, we have it to be in such a way that we have this. We have T0, T1, T2. So if we added solutes, this is what gave us the increase. So while TB is simply the change in temperature. So we use it to do T1 minus T to get it. Or you can as well say that TB plus T0 gives you T1, which is what we did here. So please, I want you to take note of this. For freezing points, that is TF, we always use KFW. We use W2 all over M2W1 times 1000. This is the generally accepted formula. So why for TB we use KFW2, that is KE. This one is Ebullioscopic constant, this one is Cryoscopic constant, all over M2W1 times 1000. Very important. So C is the same thing as that's our normal formula we are using, but it's just that on the assumption that there is always 1 mole of solute in 1000 gram solvent, it was taken that the M1, since it's happening that is equal, that it should be kept constant. So once you know this, we are good to go. That is everything on today's example. Is on elevation of boiling points and relative molecular mass. Let's see if we can solve a question on osmotic pressure. Okay, they said limitations of osmotic pressure. Limitation of osmotic pressure to calculate relative molecular mass. Okay, one of the limitations is that let's go to this. Let's get to this to avoid mistake. Come on. Listen. As a result of the difficulties in measuring osmotic pressure accurately, we do not usually use this method in calculating molecular mass. Other methods such as freezing point depression are preferred. However, when we consider solids of higher molecular masses, it is preferable to use the osmotic pressure method because the dilute solution of the substance can give an appreciable value of osmotic pressure. Such solutions that can produce an appreciable value of osmotic pressure include protein, as in found in blood cells. So if I know this, they said, what is the molecular mass of a given substance containing 2.4 grams of substance in 120 centimeter cube of water, and solution give an osmotic pressure of 9. So they're asking us to find molecular mass. Let's first remember that osmotic pressure is equals to N, that is MRT. Let's use this. That is question 14. Osmotic pressure is equals to MRT. And inside here I have N over V RT. Inside mole I have W over M. Now first let's do this. Pi. Let this V come here. So I have pi V equals to nRT. So inside this I have WRT equals to pi V. This is mass. This is molar mass. So let's try to plug. I have pi to be 998 in that question. Osmotic pressure to be 998 millimeter mercury. Then the volume, did they give me 120 centimeter cube? And first of all, if I have centimeter, remember kilometer, hectometer, decameter, meter, centimeter, millimeter. So I told you everything here is division. Why here? Multiply. So hectometer, kilometer, hectometer, decameter, meter, centimeter. So if I'm going here, it's going to be 1, 0, 0. Sorry. Meter, decimeter, are you okay? Meter, decimeter. So if I'm going to decimeter, it's going to be 1, 0. So 10 cm equals to 1 decimeter. Which means that centimeter cube has 10 times 10 times 10 cm to be in centimeter cube. And what this goes to mean is simply that if I have this to be cm cube, if I want to take it to decimeter cube now, I will simply check 1 cm. This is 1 decimeter. This is another decimeter. This is another decimeter. So this is having like 3 decimeters here. Are you seeing it? So, and I know that a decimeter cube is equals to 1000 cm. Yes? You understand? Decimeter cube is equals to 1000 cm. So what this thing means is that 10 times 10 is 100 times 10 is another 100. So if I have centimeter cube, that is 10 times 10 centimeter, this is going to give me 1 decimeter cube. 1 dm cube. So let's check that question. They said 120 centimeter cube. I can choose to use it. Or I can convert. And in converting, I'll simply do 120 divided by 1000. Very simple. So if I do 120 divided by 1000, I get my decimeter cube. But let's... So I know that 1000 centimeter cube is equals to 1 decimeter cube. So assuming the 120 centimeter cube given to me, I want to convert it to dm cube. I'll simply do 120 divided by 1000. which will be giving me, you will see this is 2 zeros now. So if I have this, it's going to give me 1, 2. So I have 0.12, 1, 2. So, but I don't want to do this. I'll simply leave my work in centimeter. If you want to convert it to decimeter cube, you are still correct. Remember that 22.4 dm cube. When you times it by 1000, you get the value in centimeter, which is 22,400. So if you know that, you can also have this for, this is the centimeter cube. This is the decimeter cube. You need to know all these things so that if you see it maybe somewhere in textbook, you don't get confused. So looking at our values, the values given to us, we have pi, which is osmotic pressure, to be 998 millimeter mercury. Then we have the volume to be 120. If you converted your own, no problem. Equals to the mass. Did they give us the mass? They said the molecular mass of a given substance containing 2.4 gram. Yes. So 2.4 gram all over m. We done of a given substance containing, so I can use M2, but let me just use M because in osmotic pressure we don't have anything like M1 and M2. So M then times R, and we know what R is. Our R is the gas constant. The gas constant. Let's check if they gave it to us. Let's check if they gave us R here. So a situation where they did not give us R, we can find our R ourselves. We can find R by ourselves by applying, since we want to use centimeter, we must convert to the 22, the dm cube to centimeter cube. So see what I mean. This R is gotten from PV equals to nRT. And our volume given to us is in centimeter. Volume is 22.4. But since it's in centimeter we will have to convert it to centimeter, which is times 1000. Then P is in 1 atmosphere. These are constants. N is 1 mole. Then R we don't know. Then temperature is 273 Kelvin. If I know this, to make R subject of the formula now will simply be divide both sides by 273 and 1. This will cancel this. 1 times all over 273. R will simply be, let's punch. So R will simply be 22,400. What am I doing? 22,400 times 1000. 1, 2, 3. 22,400 divided by 273. Should be? Okay. Then remember. Remember that this 1 atmosphere is equals to 760 millimeter mercury. And notice that if I want to use this millimeter mercury, I have to convert to millimeter mercury. Or if I want to use atmosphere, I'll take this back to atmosphere. So that means that this is supposed to be 760 in place of 1 atm. So it's supposed to be 760 since we are using mercury, millimeter mercury. So 760. So when you do 22,400 times 760, you get 17,000. You get 17,024,000. Then at the time you do what you have, let's say we do 17,024,000 divided by 273. So 17,024,000 0.024000 divided by 273. You get 600 and okay, you get 62,358. Yes. So you get 62,358.97 as your gas constant. And remember that this one is in millimeter. Millimeter, mercury, then centimeter, all over Kelvin, or you say K, all over K. And this one here, okay, K then times mole, because you have mole here coming here too, because these two are supposed to come and divide. All right, so this is what I have for my R. This is what I have for my R. So this is how I'm getting R if it's not given. It's supposed to be given. So I'll just come here and put it. So I have 62359 times temperature. I use this Kelvin, so I will maintain it. This is 16 degrees. I have to convert that 16 degrees to Kelvin. And when I do it, because I used Kelvin to calculate, when I do 16 degrees C plus 273, you get first of all 280, 286, 789, 289 Kelvin. So then times 289. So by the time you punch, what you get? So if I punch this, I will get, let's do it. If I punch this, I will get let's do 2.4 times 62359 times 289. I get 4352. That is 252,202.4. All over M is equals to 998 times 120. I get 119,760. And you know that, you remember that anything standing on this one is over 1. Cross multiply, you get 119,760 M is equals to 4325,202.4. Divide both sides by 119,760. So M is equals to, so let's do it, 43252, then 202.4 divided by 119,760. So you get M to be 361.1573. So the molar mass is approximately 361 gram per mole. So 361. So in some textbooks you can see this to be approximately 361.2, but I'm leaving mine as 361 gram per mole. So that is your answer. There you have it. That's how to find the osmotic pressure. So one of the things you need to note about the osmotic pressure is that when you are solving to find R if it's not given, you need to make sure that whatever they gave you osmotic pressure to be, that's where you are converting your pressure to be when you are using this ideal gas to find R. Notice that they gave me osmotic pressure to be 998 millimeter mercury. So the pressure I'm going to use is 760 millimeter mercury. Assuming they gave me this to be in torr, the pressure I will use will be in torr, and 1 atm is equals to 760 torr. Then, since the centimeter cube is what I'm given, the volume is not going to be in 22.4, but rather in 22,400, which I even showed you how to get from here. So with that said, let's check if there's any other question we can look at. This time, let's look at one with freezing points. Okay, they said 2 solutions containing respectively 7.5 gram of urea and 42.75 gram of a substance X, each in 1000 gram of water, freeze at the same temperature. Calculate the molecular mass of X. Okay. So, alright, for question 12. 2 solutions containing, that is, one is urea. They gave me CONH22. Then they gave me, this one is containing 7.5 gram. While solution X is containing 42.75 gram of a substance, each in 1000 gram of solvent. That is, H2O is 1000 gram, and H2O, this is W1. This is W2 solute X. Then this one is W2 of urea. So let's do it in such a way that we have this to be solute. So this one is urea. So 2 solutions inside water, 2 solutes inside water. Then they freeze at the same temperature. So their TF for the both of them is the same. They say calculate the molecular mass of S. That is M2X is what we are finding. Alright. Is there any other thing we need? Okay, we need to find M1, which is the same thing as saying one times 2 plus 16, which is equals to 18 gram per mole. 18 gram per mole. Very important. But remember that anytime you are solving freezing points, that is change in freezing points, that we normally make use of KFW2 times 1000 all over M2W1. We say that we take the molar mass. If you remember, I've talked about this before. We take the molar mass of solvent to be constant. Molar mass of solvent to be constant. We take the molar mass to be constant. There is no need checking it. It's always constant. So we are not using it. We always take the molar mass of solvent to be constant. We are not using it, and we are not looking for it. So this is what we have. Very important. So whenever you are solving boiling points and freezing points, always know that the molar mass of water, you don't use it because it's constant. Constant in the sense that it is equal. It is of use. So there's no, we know it. So there's no use using it. So we don't use it to solve. So we simply make use of this. If not, it could have been here. So I will now have, for the first solute, remember that is always going to be is always, the idea is always going to be, this formula makes provision for solvents and solutes. And it's the same thing as saying one solvent and solute. So that means that in this case, I'm going to use this formula 2 times. Very important. If I have, so note it, note. If I have 3 solutes, I'm going to use the formula such that I have the first solute plus solvent, solute plus solvent, then solve again, solute 2 plus solvent, solute 3 plus solvent. Using the formula, I will solve it because the formula makes provision for just solute and solvent. So if I'm given 2 solutes, I have to solve solute 1 with solvent, solute 2 with solvent. Then at the end of the day, I will equal everything and then find maybe the molecular mass I'm asked to find. It's not something strange. Reason is that the formula for finding freezing points makes provision for you finding the solute and solvent, solute and solvent, solute and solvent, not solutes and solvents. So it's more like solution with small solute and solvent. And remember that this particular method has limitations when finding molecular mass. It has its limitation, its downsides and highsides. So let's find for the solution 1, which is urea. So for M2 of urea, I will simply use this formula to do, to find the M2 now. That is M2 of urea. M2 urea. I'll simply have this to be, since it's given, it's going to be C plus that is 12 plus 16 all into, let's check what they gave me for nitrogen. So all into nitrogen, they gave me 14 plus 1 into 2. Then everything here is getting multiplied by 2. So let's do the maths. Let's do the maths. So I have 12. I have 12 plus 16, 28. Then I have 14 plus 2. 14 plus 2, 16. So I have 16 and everything is getting multiplied by 2. So 16 times 2, that should be 32. So 16 times 2, 32. So 32 plus 28. 32 plus 28 should be like 60. So I have 60 gram per mole. So plus, I've taught you something like this before in class. I wanted to express this that day. That particular year was asking a lot of questions. So I get 60 gram per mole for urea, M2 for urea. So let's plug it into this. So I have change in TF to be equals to KF is given to me. Was KF given in this question? Let's check. Okay, KF was not given, but we can find KF. We can actually find KF. KF was not given, so let's just write things out. So I have KF not given. We know we can find KF by using our cryoscopic constant. So then W2 is given, that is weight of the second solute now is given, which is 7.5 gram. If you like, don't put mind. Be saying you don't understand. So 7.5 this is it. We have two solutes. I'm calling this one W2, weight of solutes, urea. Then this one W2, weight of solute, X. They call that one X. So I told you that since the formula made provision for solute and solvent, if they give you two solutes, you have to solve for it differently using the formula. They give you three solutes, you have to solve 3 times using the formula. So times this times 1000 all over M2. M2 that we just got now for urea is 60. Then times W1, weight of water there, that is mass of water, times 1000. So we don't know the Kf. We don't know the Kf. We can actually use, did they give us can actually use this to be 0.52, or we just leave it. Let's say at this point, because I know that whatever I find, I must equal it. Let's say at this point I've gotten I've gotten data TF, change the freezing point, for urea and solvent, that is H2O. Now let me get for solute X, that is for solute X and solvent. I will apply the same formula, which is change in TF is equals to Kf W2 times 1000 all over M2 W1. So this is going to be the sentence saying change in TF. And did they give us they said they freeze at the same temperature, but they did not give us the temperature. So I will have equals to Kf W2. This time around is that of solvent X, solute X, sorry. So, and the weight there is 42.75. So 42.75 times 1000 all over M2, the molecular mass, or the molar mass of X. Look at it, we don't know it. That's what we are looking for. We don't know it. This is for urea. This one we don't know it. So I just write M2. Then W1 will always remain the weight of solvents, or mass of solvents, which is 1000 times 1000. So what you just do is, if they give you so many solutes to solve, by the time you finish solving, that's why I didn't bother putting Kf, because certain times when you're solving a question, you already know how the question goes. So when I have more than one solute to solve for, by the time I finish solving for the first one, solving for the second one, I'll now come and make it that this is for urea. Let's say I put this for urea. Then let's say I put this one for X. I'll come and make it that since they freeze at the same temperature, I will have change in TF of urea is equals to change in TF of X. They fixed at the same temperature. Remember, that's what the question said. So remember the question. They freeze at the same temperature. So since they freeze at the same temperature, their temperatures are equal. So what I just need to do is to equate the values. So I have here Kf times 7.5 times 1000 all over 60 times 1000 is equals to what I have here, Kf times 42.75 times 1000 all over M2 times 1000. So you can very well see that just mathematically you can start saying, what do I have here and what do I have here? I have 1000 here, I have 1000 here, cancel. I have Kf here, I have Kf here. I have 1000 here, I have 1000 here. What do I have left? I have 7.5 all over 60 equals to 42.75 all over M2. So whenever you are doing freezing point or boiling point, this thing is not plenty. It's all about, you know that relative lowering of vapor pressure don't give you this stress. Boiling point and freezing point, once you are doing it, you make sure that you keep M2 constant, that is molar mass, M1 constant, that is molar mass of solvent. You keep it constant. Once you keep it constant, it means that you're using this formula. Stay applying the same formula from the point where we initiated it, the same. So if you know that once they give you more than one solute, if it's 3 solutes, you use the formulas to solve for solute and solvent, solute and solvent, solute and solvent. At the end of the day, if they said it happened at the same temperature or freezing point, once you're giving this kind of thing, it will always be the same, because for it to freeze, the two things inside there, they have to freeze together. So at the point when you finish it, you equate it. If you equate, you can now cross multiply, so that you now have 7.5 M2 is equals to 60 times 42.75. And when you punch, here's my calculator, and when you punch this, good. When you punch this, you now have 60 times 42.75 is going to give you 2565 is equals to 7.5 M2. So divide both sides by 7.5, the coefficient of M2. So you see that M2 is simply going to be 2565 divided by 7.5. So you get 342. And this is molar mass you are calculating, so it's going to be gram per mole. Which means that this X, 342 gram per mole. Remember, we did something like that earlier when we did for this. That gave us 342. So this is likely sucrose C12H22O11. So because that's the same thing we are getting. And remember that colligative property, to find relative molecular mass, you have to be focusing on compounds that are organic compounds. So we have 342 gram per mole. That's our final answer. So we'll stop here for today. In our next class, we'll look into more questions like this. Thank you very much, and God bless you. Please subscribe to the channel.